write y is function of, let me write like this, p r, or let me use small, let's a little better, p r beta delta a delta r. Then you know that Cy, which I can define as y by half rho v square s into b. This is to be noted for CL. For CL and CM, the characteristic length was mean aerodynamic chord, but for all lateral directional coefficient, the characteristic length is b, the span. Right? That's why b has come. So this is again, I can write function of p r beta delta a delta r, right? So that you don't get confused, I write f star something, or let me delete this. Okay. So Cy is function of this, so I can expand Cy as Cy naught plus dCy by dPb by 2u1 into Pb by 2u1. You understand why we are using Pb by 2u1, because we want to non-dimensionalize roll rate, right? Plus dCy by d, again r is a rate, so Rb by 2u1 into Rb by 2u1 plus dCy by d beta into beta. There is no need to multiply it by b and divide by 2u1, because beta itself is dimensionless. Similarly, dCy by d delta a into delta a plus dCy by dr d delta r into delta r. In a short notation, we can write this as Cy equal to Cy beta into beta plus Cyp into Pb by 2u1 and Cyr, Cy delta a and Cy delta r, where Cy is side force y non-dimensionalized with dynamic pressure half rho v square into s. Right? If I know this, I can easily write the expression for Cl and Cn. What is Cl? Cl is rolling moment non-dimensionalized with half rho v square s, but it's a rolling moment, so a length term is required, so it is b. Please note that for longitudinal case, the characteristic length was c bar, but for lateral directional case, the characteristic length will be the span b. That's b is used here. So this I can easily write again Cl beta into beta plus Cl p into Pb by 2u1 plus Cl r into Rb by 2u1 plus Cl delta a into delta a plus Cl delta r into delta r. Okay? Similarly, I can write for Yawing moment coefficient Cn, which is nothing but Yawing moment non-dimensionalized with half rho v square s, what? B or C? It is directional case, it is B. Okay? Is equal to, I write again, Cn beta into beta plus Cn p into Pb by 2u1 plus Cnr into Rb by 2u1 plus Cn delta a into delta a plus Cn delta r into delta r. Please understand, this sort of an expansion strictly true for low speed and moderate performance airplane, where we are assuming everything to be linear. Today's modern aircraft, the airplanes are very high performance with high rates, high angle of attack. So there, writing or expanding this in terms of linearized concept may not be true, unless and until you cleverly, judiciously, locally linearize it. But there are different ways of handling it. Okay? So that should be kept in your mind all the time. So now, if I erase this to make the board clear, so I write this is C L. So this is CL, this is CN. It goes without saying that we have put CL naught and Cn naught identically equal to 0. Okay? Now see here, before you do anything, if you play any game with this derivative, let us be sure we have understood this in terms of their sign. In stability, many times, perhaps most of the time, one should be very, very careful about the sign. The sign decides more importantly than the magnitude. For example, dCm by dCl should be less than 0 decides longitudinal static stability. Right. Cn beta greater than 0 decides directional static stability. Cl beta less than 0 decides lateral static stability. It is the sign. The magnitude decides the control part of it, right? If this is very large negative, means highly statically stable. So if you want to change from one trim to another trim, a lot of effort you have to put. Similar thing, if Cn beta is large, that means it will become very sensitive to crosswind. Similar Cl beta, you understand that, right? So if I want to cross check whether I understood the signs or not, let's take one by one. Cy beta, what will be its sign? We'll draw a tile like this, and positive beta means wind is coming from the right hand side and flying like this. This is the relative airspeed. So if this is positive beta, and you know that your x, y is here, z is here, so the force of the vertical tail will be opposite of y, right? So the sign of Cy beta is less than 0. Is this clear? I want to demonstrate the sign of Cy beta. Suppose this is the vertical tail. I am moving like this, and let's say this is the relative airspeed. Then the side force on the vertical tail will be this direction. Where is my y direction? Y is x is this, y is this direction, and force is in this direction for positive beta. So Cy beta becomes negative, right? Next is Cyp. If we take only vertical tail, please understand these signs of the whole derivative should be seen as a combination of all the components. We are discussing about the sign of Cy beta, and we have seen that Cy beta because of vertical tail will be negative, but at this point, please understand Cy beta will have a component because of Cy beta of vertical tail, Cy beta of wing, Cy beta of fuselage, all this, right? So we have to check each and every component how they are going to add. I am only giving an illustrative example. I am using vertical tail for most of the time because that contributes the maximum for most of the cases. So Cy beta less than 0 you have understood. Now Cyp, if I again try to see what is the vertical tail contribution, you could see that if this is the vertical tail and P positive mean right wing going down like this, so this is pushing the air downward, and this fin will experience force in this opposite direction, right? Okay, in this direction. So y is this way, so force is in this direction. So again Cyp because of vertical tail is less than 0. But with wing and sweep, it may change the sign, right? I am talking about vertical tail. Then comes Cyr. Again Cyr, you see, this is the airplane, this is the vertical tail, positive R is this. Okay? So this tail is pushing the air this way, it is experiencing force in this direction, and y is also in this direction. So Cyr is greater than 0. I repeat, as it takes positive R, this vertical tail is pushing the air this way, and it experiences force in this direction, and we know y is in this direction, so Cyr is positive. And then Cy delta R, you know what is delta R positive? Delta R positive is towards left, like this, deflected towards left. I am moving like this, the force will be coming in this direction, the vertical tail will experience the force in this direction, which is along the positive y direction, so Cy delta R will be positive. Okay? Please use pen and one paper like this and try to cross check these signs. What I am talking here, let's not forget, all this I am taking the contribution of vertical tail. Okay? However, we know the overall contribution has to be seen. Right? Now coming back to CL, in CL you see there is CL beta, and the moment CL beta comes, if I want to check the sign, if you know CL beta contribution would be because of CL beta vertical tail, CL beta wing, CL beta fuselage. At least here we know that if it is a high wing, CL beta because of wing, CL beta because of wing will be less than 0. That is contribution of wing. If it has a dihedral like this, again CL beta, wing contribution will be less than 0. And if it is a low wing like this, then of course CL beta is greater than 0. This much we know. For vertical tail, let us see what happens. If this is the vertical tail, CL beta means it has banged, started side slipping. So as it side slips, force will act on the vertical in this direction, and that will give rolling moment about center line, and where the left wing will go down. So again that is a negative sign. So CL beta less than 0 when you are talking of vertical tail. Then comes CLP. What is CLP? Extremely important. CLP. This is DCL by dPb by 2U1. This is also called roll damping. Remember for longitudinal case, similar was CMQ, which was pitch damping derivative. Okay. So let us see what is CLP, who are the prime contributor. Here the wing is prime contributor. For CLP, prime contributor is wing. What happens? Suppose this is positive P, I am flying into the board, and positive roll rate means right wing going down. What you see here? At each point at a distance r, this will see a vertical component of relative air, which is P into R, right, omega r. This divided by U1, let's say moving the forward speed, that will give you an approximate angle of attack at each section. So this will, in cumulative way, generate a force in this direction, which will be proportional to alpha, delta alpha here, which has P. So this will be proportional to P, roll rate. Similar thing will happen here in reverse direction, right? So this will in turn give a rolling moment. It will give a rolling moment, and which will be proportional to P. That's more important. Okay? And you know the reaction moment proportional to P or proportional to the rate, correct, is proportional to the rate, we attribute it to damping derivatives, right? Or it causes damping to the dynamics. As we have seen for second order system, Cx dot plus Kx equal to f of t. You see this one, Cx dot. So here we see that the moment it tries to bank like this, just immediately there is a moment to opposite, and that opposing moment is proportional to the rate, and that is why this is called roll damping, and primary contributor is wing, and obviously the sign CLP is negative. For a positive P, right wing going down, moment is this way, left going down, so CLP is negative. As CMQ for longitudinal case was negative, and both are damping derivatives. This one for lateral case, this is for longitudinal case. Okay. So CLP is okay. What about CLR? Let us see what is CLR. Once CLP is over, now look for CLR. What is CLR? CLR is dCl by dRB by 2U1. That means question is, if this body is having a yaw rate like this, which is a positive yaw rate, right wing going back, will it create a rolling moment as a reaction or not? You see, very simple. As it rotates like this vertical tail is pushing the air this way, so it will experience a force in this direction, and that force will be somewhere at the center of this fin or vertical tail. So that force into the distance between the force and the center line will give me a positive rolling moment. That is, if this is the fuselage, this is the vertical tail, as it goes for R is positive, or R is positive, at the right wing going back, so there will be a force experience in this direction, and this force into this y bar will give me a positive rolling moment. So CLR is greater than 0. Sign by CLR is greater than 0. I repeat again here, if this is the vertical tail, if it is having a positive R, the yaw rate like this, as it moves like this, tail will push the air this way, so it will experience a force in this direction. Or let me show it. I repeat, as this body having a positive R, the right wing going back, this tail is pushing the air that way, so the tail will experience a force in this direction, and this force into this distance, the offset from the center line, will give a positive rolling moment, and that is what? Positive CL. So that is why CLR is greater than 0. Okay. Once CLR is over, then Cy delta A and Cy delta R, that is straightforward depending upon which way you are deflecting the aileron. You know, if this is my wing, if I put this aileron down and this aileron up, then I will bank like this. So if I define this combination as a positive delta A, then CL delta is negative. If I define other way, the CL delta A will become positive. So depending upon delta I sign, you can pick positive or negative. But as far as CL delta R is concerned, you know that delta R, if this is the rudder, delta positive is this, towards left looking from the top, and I am moving forward. As I deflect like this, force will be in this direction. So this force into the distance from the axis will give me a positive rolling moment. So CL delta R is greater than 0. This is very simple. If I deflect towards left, force will be in this direction. This force into this distance, y bar, which will give me a positive roll when I am moving in this direction. Right? So CL delta R is positive. I repeat here again with this small example. If this is the fuselage, this is the rudder, I deflect it like this, which is positive by convention, which everybody agrees. So then as it moves forward, the force is in this direction, and this force into this distance from center line will give a positive rolling moment. That is why CL delta R is positive. Now let us talk about Cn. If I come to Cn, let us see what is the sign of Cn beta. Cn beta, you have no confusion, it has to be greater than 0 if it is statically stable in directional case, right? What about Cnp? Again, if I talk about contribution of vertical tail, let's see what happens. This is the body and this is the vertical tail. Cnp, that is, if I give a P like this, roll rate, how the yawing moment will generate. As I roll it like this, you could see that the vertical tail will get a force in this direction, and that force and CG sum over here will give a positive yawing moment. Am I correct? Cnp, P is this, as it is going P, vertical tail will get a force in this direction, which will give a yawing moment positive. So Cnp is greater than 0. Cnr, what is Cnr? You know Cmq, damping in pitch. Clp is damping in roll. So Cnr is damping in in yaw, right? So, this is again for a statically stable airplane CNR is negative less than 0. And then if I talk about Cn delta R, you can check yourself if this is the fuselage, this is the rudder, and this is a positive towards left. As I move forward, the force will be like this in this direction, and this will give a yawing moment about CG in the negative way. The force is there, point is here, so it will give moment like this, yawing moment negative. So, Cn delta R will be less than 0. Okay. This understanding of the signs are extremely important, and please understand most of the cases I have shown the contribution due to vertical tail, and wherever wing played an important role, dominating role, I have mentioned it. But in practice, you have to see the contribution because of all the 3, 4, 5 components, right? That may have propeller also. Okay, that becomes an involved thing. But you as a flight dynamics man should understand that I need to be bothered about these derivatives. Because why? You understand that finally, when you are going for dynamic stability study, that stability matrix, remember this a huge one, took a lot of time to write, and from after taking Laplace transform and all, this matrix is constructed with these derivatives, and if they are not correct in sign and magnitude, that stability matrix will be altered, right? And then you will get some fictitious result. So, that is why before you go to that, I thought a revision on this will be extremely important. Okay. In the next class, we will go for developing short period equation of motion pertaining to lateral directional case. Thank you very much.